Uh, have you looked at the exam yet?
Not at all. Did I? I usually okay, sure.
I am flying out.
Okay.
Uh, yeah, I think you and Vanessa are last semester.
Okay.
We've talked about matrix and stuff. Gamma algebra. Yeah, we'll add those.
That's good. Yeah, my life was totally consumed by faculty hiring.
Yeah.
It was. Yeah. All right.
We figured it out.
What was it?
It was there were two kinds of rotate
Yeah. All right. There was a slight subtle difference. Oh, in the rotation operation. Sounds like we need some tests for rotate left and right, separate from the rest. I guess to go show that unit testing is beautiful. All right. Sure. Wow. Yeah, let me adjust my microphone volume. Okay. Hi. Okay, cool. We're gonna talk about minimum scanning trees. Hello, Dave Moore, Spring Grateful. Interesting that it's quiet here because I had the busiest office hours I've had all semester today. So it goes. So today we're going to be talking about a cousin of the shortest path problem, the minimum spanning tree problem. I'm going to start with a little warm-up. It's not related to minimum spanning trees, but it'll get our brains thinking before we get to the problem of it. So I want you to think about this question. If we have a graph that's undirected, how do you know if it has cycles? You can use anything you know from the class so far, and I'll give you a minute to think about this. You run some kind of search, use some data structure somehow. Oh, thank you. Thought I did that. But I didn't. All right. Someone want to give a suggestion? Yeah? Right. Use DFS, and if you see something that's already marked that you didn't just come from, then there's a cycle. That's one approach, right? So just search DFS. If you see something that's already marked, you know you've been there. Just make sure not to look back where you just came from. And this will take V plus E time. Any other ideas someone had? I'll give you, oh yeah. Oh, you could count edges? I mean, yes, that could give you at some point, if you have too many edges or too few edges, you know there exists a cycle, but that's not a foolproof way. Here's a second approach, which is to use a weighted quick union object. So just iterate over all the edges, and every time you look at an edge, you check if it's connected. If it's not connected, you union them. And if at any point you see an edge where the two sides are already connected, then there's a cycle. This approach would be V plus E times inverse Ackermann log V time overall. Okay. But both of these approaches are fine. This one's a little more straightforward. This one's also pretty and a bit faster. Wait, actually, no, a bit slower, barely slower. All right. Okay, let's talk about minimum spanning trees. So a minimum spanning tree is going to be defined as follows. If we have an undirected graph, first I'll tell you what a spanning tree is. It's a subgraph of the original graph. I'll call this thing T for tree. And it needs to be connected, meaning all the vertices are reached by in this subgraph here. It's acyclic, no cycles. And it includes all of the vertices. These top two things make it a tree. And the fact that it includes all of the vertices makes it spanning. Okay, so all the vertices are connected by some edge. So this right here, this is an example of a spanning tree, but there are many spanning trees, of course. Now, a minimum spanning tree will be a spanning tree whose total weight is the smallest possible in the graph. An example of this is imagine you're laying power lines between buildings, and this is the cost of laying a line between these two buildings. If I don't care about redundancy, and all I want is the minimum total cost of wiring to connect every building, this would be the lowest cost way, assuming this is the minimum spanning tree. I wouldn't want to run a wire between these two buildings. It's too long. Okay. So it has a natural reason it might exist. You could use this for planning infrastructure. And we'll talk about some other applications in a moment. So these are other spanning trees. Notice that in both cases, we have a subgraph that connects all the vertices, and there's no cycles. In this particular case, this is a degenerate tree, because it's just a line, but or a path. But a path through all the vertices is indeed still a tree, just degenerate. Question for you. Which of these are spanning trees? I don't pick the yellow keys, just some random word. Wait for a few more responses. All right, top left one. Is this a spanning tree? No, why? It's not connected. Every vertex is included, but it's not, we don't have a path that connects any two vertices. This one? No, why? Cycle, right. This one? Great, okay, you're correct. So it's just one, just the bottom one. So what good is a spanning tree? You could use it for planning infrastructure in principle. It's kind of weird because you're assuming you don't care about redundancy, which of course you care about in real life. There's other things like classic handwriting recognition algorithms. Before we had neural networks to do all of our business, there was a spanning tree based algorithm where you would find little centers of mass of people's writing and so forth. I don't know how this works exactly, but here's a link if you want to learn about ancient history. On the right, here's an example looking at nuclei of cells, the arrangement of nuclei in cancer cells. And it turns out that there's hallmarks of the spanning tree that could be used for detection. Now, again, in modern machine learning, it's less common that you'll do something like pre-processing using like a clever technique, because often you can just provide the raw image and the neural network is flexible enough to find the pattern. That's not always true. And there's still people who feel like sometimes domain knowledge is going to get you better basic features for your model. But these are some classic examples of why spanning trees are important. Another reason, though, is they're just an interesting mathematical object in addition to their potential real-world uses. Okay, so how do we find a spanning tree? Or how do we find the minimum spanning tree, really? I'm going to introduce something called the cut property. This is the part where we really need to focus. After this, it's kind of not so bad, but this is the part where we're going to drop some terminology on you and some ideas that are pretty important. So the first thing I'm going to tell you about is what a cut is. So given a graph, it has V vertices. A cut is just an assignment of the nodes to two non-empty sets. So here I have the white set and the gray set. Soon we'll have the green set and the white set. But the point is you just color every vertex one of two colors. And a cut will be any pair of non-empty sets. So roughly 2 to the V, slightly less, cuts exist. A crossing edge is any edge which connects nodes from the white vertex set to the gray vertex set. Here I have 1, 2, 3, 4, 5, 6 crossing edges for this specific cut. Question, how did I get these 5 vertices being gray? What do you think? I just picked them arbitrarily, okay? So any other assignment of gray and white, also a cut. This is just the one I picked because it's from the Princeton textbook where I borrowed this figure. The cut property is what we're going to use to prove that all of our different algorithms for minimum spanning trees today work. It says that given any cut, so you just throw gray darts at the graph and throw them at the vertices, the minimum weight edge, which crosses the cut, is going to always be part of the minimum spanning tree, assuming the edge weights are unique. The edge weights aren't unique. You can say at least one of them is part of the minimum spanning tree, but we're going to assume unique weights, meaning no 2 edges have the same weight, and it'll make our life easier. If you want, you can think about duplicate weights later. It's not that much more interesting, but it is harder to follow in lecture. Okay. So question for you, is this a valid cut? Yeah, actually, it's fine. They do not need to be contiguous. Nowhere did I say that. So purple, 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 any set of purple vertices would be valid as long as it's non-empty. If you have all white or all purple, that doesn't count according to this definition. So the question now for you is, what edge is the minimum weight edge crossing this cut? So first you have to figure out what are the crossing edges, and then you need to figure out which one's the smallest. Over here, I have the weights of all of the edges. Good luck. Okay, I'm gonna give you a hint if you don't know where to start. Does the edge between 1 and 7, is that crossing the cut? No, why? It's connecting 2 white vertices. Continue. We haven't gotten it yet. So 1, 7 doesn't count because both edges or both vertices are white. This thing working, by the way? Oh, sorry. I'm setting the things you can actually respond now. Sorry. Okay, now you can respond. Okay, continuing with the thought of giving you hints. What's the minimum weight edge in the whole graph? 0, 7. Is that a crossing edge? No. Okay, well, what edge do you might consider next? 2, 3. What about that one? No. Okay, about 1, 7? No. Okay, about 0, 2? Yeah, that one's fine. So the answer is this one. All right. That's how to think about this problem. Any questions about this definition? I haven't proven to you that the cut property is true, but what I can tell you about this is that this edge right here is part of the minimum spanning tree for this graph, guaranteed. Okay. Now that might seem kind of weird. I picked a random coloring. These 4 vertices are purple, but I can promise you, and I'll prove it in a moment, that this edge, even though this is a random coloring, will be part of the global minimum spanning tree. Any questions about yes? Would there ever be impossible cuts? No. I mean, like, oh, you're saying, like, could I show them all purple? Oh, I see what you're saying. If I always color, I'm assuming my graph is connected. Because if it isn't connected, there's no such thing as a spanning tree. So yes, for any cut, there's always a crossing edge, as long as the graph is connected. Any other questions? Okay. So let me now tell you why the cut property is true. So no matter how I color my vertices, the minimum crossing edge is always going to be in the minimum spanning tree. It's a cute proof by contradiction, a little more 70 flavored than our class usually is, but here's the idea. let's say X is the minimum spanning tree. So we know we have some minimum spanning tree. It's a collection of edges that connects the graph that doesn't have a cycle. And let's suppose that the minimum crossing edge E for some cut is not an X, okay? Well, what I can tell you, here's a little picture here. This set of dark lines, including this red one, that is X. That's the minimum spanning tree. We're assuming that that's the minimum spanning tree. And now as an example, let's say we assign these vertices here to be gray and these to be white, just arbitrarily. And let's say that we have an edge E, which crosses the cut, the gray and the white, and it's not in the spanning tree. Here it is, look at it, okay? So first thing I want you to think about is to notice that if I add E, it will create a cycle. Okay, why is that? Well, I have my gray vertices over here, and I have my white vertices over here. And if I have a cut, is there always a crossing edge between both sides of the cut? What do you think? Yeah, because it's a spanning tree. So there had to have already been a path across. And if I add another path across, it's basically you went in from the gray side of the cut to the white side, and now you have a way to get back out. And the only way that's possible is if there's some cycle. So if I add another edge, there's going to be a cycle because there's a way in and a way back out. Okay? Now let's say F is the other edge that crosses, right? So E is the crossing edge that we just added that's smaller, and F is the old one that existed. Now, hopefully you agree that F existed because we had a gray set of vertices and a white set of vertices, and F used to be the bridge between them. Now we have another bridge. If we were to simply take the old bridge, F, toss it away, and now we have E instead, that gives me a lower weight spanning tree, and that's a contradiction. Okay, so if you have a minimum spanning tree, where for some cut, the minimum crossing edge is not in the spanning tree, you can just replace the old crossing edge with the smaller one. Then you get a smaller weight minimum spanning tree. So that means the original X was not the minimum spanning tree. Okay. It's a bit of a subtle argument, but hopefully it's clear. And if not, you can watch the internet version of me say it slightly better than that. Okay. So this tells me, so if you didn't totally follow that, that's okay. You could just set that aside like a little below the level of abstraction for what's engaging with your cognitive gears right now. And you could say, I'm just going to trust that the cut property is true. If the cut property is true, then there's an easy algorithm for finding a minimum spanning tree, which is to throw random colors at all the vertices, and now they're purple, let's say. And then you find the smallest crossing edge, and you add that to your minimum spanning tree. Then you color all the vertices randomly again, and you take the next smallest edge. Occasionally it'll be redundant, right? Because you'll just happen to get a crossing where that is the smallest edge. And you just keep repeating this process until you have V minus 1 edges. Why do you stop then? Well, V minus 1 edges is how many you need to have a tree, similar to when Justin was talking about shortest paths trees. Now this should work, but it's going to be slow and like ugly. Like it's just generating random cuts and finding minimum edges. So we're going to do something better than random. I'm going to go one more level in, and then I'll take some questions because I want to try and anchor things to make this super clear with the specific algorithm that you can see with your eyeballs. So let's talk about Prim's algorithm, which is the basic, most simplest, I think. Well, actually, they're both pretty similar in complexity. This is Prim's algorithm. And how it's going to work is we're going to pick some arbitrary start node, and then we're just going to grab the shortest edge that has at least one node inside of the minimum span. Sorry, that has exactly one node inside of the minimum spanning tree. And we're going to repeat this process. Let me show you vision. So I'm going to start arbitrarily from A. And at that point, when I pick A, I have two cuts, the white side and the green side. Which of these two edges should I choose? C, right? The one that goes to C. So I'll set edge 2 for C to A. Okay. Now I'm going to consider how many edges. 4 different edges. There's 4 different edges that cross from the minimum spanning tree we have so far, the minimum spanning tree under construction, and the rest of the graph. Which edge should we choose? 1, this one that goes to E, right? Okay. All right. How do we know this right here is part of the minimum spanning tree for the whole graph? That's the cut property. This is the white side of the cut. This is the green side. So we know it has to be part of the minimum spanning tree if we trust that proof. Now we're going to consider a bunch of edges. Which one gets added next? Now this is a little tricky. I'm kind of like being mean. You'll notice they're not unique, but what do you think we should add next? B or D. Either one would be fine. There's two edges of weight 2. We didn't really talk about what happens here, but I'm exposing that little detail. I'm going to pick D. Okay. You could also have picked B, and it's guaranteed to work as well. I'll leave this as an exercise if you want to think about it, but it's not the key point for what we care. Okay. So at this point, we now have a cut where we have lots and lots of crossing edges. So it is true that B is a little island over here, but this is still a valid cut. Cuts don't need to be contiguous in the graph, the green vertices, or equivalent of the white vertices. Now we're looking at many edges at once. Which one should we use? This G vertex. Now, some of you might think this seems inefficient because it's so many edges to be iterating over, and we'll fix that in a minute, but we're going to pick G here. All right. Now we consider even more edges. We pick. So we're only looking at the magenta edges. Which one's smallest? F. And so how do you get to F? We're going to come from G. And then lastly, we have these, what does this value become right here? What's going to go in this box? A, right. And then we're done. So that's the minimum spanning tree. All right, any questions about what we're doing so far? Yeah.
So to clarify, the minimum spanning tree only says like what the minimum distances are. Like, so does it work for, we know that the minimum distance between A to F has to cover that route through the minimum spanning tree?
It's not necessarily the case that the path from A to F that's shortest goes through this whole path. It happens to be true in this graph, maybe. But in general, it's the total weight of the entire spanning tree is minimum. Not that any individual path between two vertices is minimized. Yeah. That would be Justin's algorithm, the Dijkstra's algorithm. And in that case, it's only from the source, not from any vertex to any vertex. Okay. So that's a conceptual picture. So why does this work? How do we know it's correct? Well, it's just a special case of our generic algorithm. We start with a cut, which is only the start vertex, and the green vertices is everything not connected to start. And then we add another vertex. And every time as we bring in more vertices into white vertex club, that just forms a bigger and bigger set, white set. And then over time, you're just doing the same thing. It's just instead of random cuts, we're picking intelligently. We're growing a cut from the source. Okay. Now, the thing I didn't like before is that iterating over a bunch of magenta edges is slow. So we could be a little clever and use the priority queue to speed things up. And it turns out we'll have something that's almost identical to Dijkstra's. It's just the way in which we think about the algorithm is a little different. Instead of with Dijkstra's, it was the distance from the source. Now it's going to be the distance from the tree. So Dijkstra's is distance from source. Prim's is the exact same thing, but distance from tree. So let's try running through it. So first, we're going to insert all of the vertices into the fringe, just like we did with Dijkstra's algorithm. These are all infinitely far away. And then we're going to relax these edges from A. And so what distance am I going to get for B now? 2. Okay, so B is going to get a distance of 2. And what's edge 2 going to be? A, right? And what's C's distance going to be? 1, and edge 2 will be A. Okay, good. We're done so far. Could these change later? Yeah, maybe. Not until we remove them, though, from the fringe. Okay, so now the fringe is ordered in distance from the source, so we're going to do C next. I'm having dotted lines here to basically indicate this is like conditionally the best edge. But until I delete this vertex off of the fringe, I'm not committed totally that this is the right edge. This is similar to how we saw that with Dijkstra's. Like an edge, you may change the distance and the edge to for a specific vertex multiple times. And we'll see that at some point in this demo. So who do we pop off of the fringe next? C. And then we consider its 3 edges. So when we relax this edge, does anything happen? No. This one? Yeah, that one becomes 1, and this one becomes 15, right? Notice that's a little different than before. With Dijkstra's, what number would this have been? 2, and this one would have been 16, because those distances, the fringe values represented the distance from the source. Now they're the distance from the tree. Okay. Notice that the edge 2 for F is C. Do you think this will still be C at the end of the algorithm? No, probably there's a better way to get there. So that's again why I have this sort of provisional dotted line that indicates what the current edge 2 is. And once something is firm, I'm bolding it. It's kind of hard to see that it's bolded, but it is. So who do we go to next? E. And so spiritually, why? What is it about E that makes E the best choice? The shortest cross. I think of it as it's closest to the tree, which is, yes, closest to the spanning tree that we have built so far, but equivalently, you could say it's the shortest crossing edge. Great. So now we do E next. And so if you're a webcast viewer, you can find the distance to edge to and fringe after the next relaxation. And I'd like you to maybe pick two of, oh, wait, okay. Did I give them away? Yeah, maybe not. Okay. So what I'd like you to do is think about, at least among these edges we're going to consider, what's one of them that changes. So just try and, in your head, predict one of the changes over here for a minute. Maybe to make it specific, what will F's row look like? So what does the fringe look like? What does this value become? What does this become? So what's going to happen? Let's focus on the F. So what number will this become? 4, right? So this is going to become a 4. Will this number and this here change? Yes. And why is it important that number changes down here? Because it tells the priority queue like when we're going to rope in F and start thinking of F. This number right here also changed to 4, and this will change to an E. Okay. So that's all the changes that happen. So if you're a webcast viewer and you came up with that, great. And these are all the changes from these 4 edge relaxations. This one didn't change because 3 is bigger than 2. Okay, any questions? Yeah.
Big difference to what we did last time is that we're adding shorter between
I think that the question, what's the difference between what we were doing before with the conceptual picture and here? This one, the difference is that by using a fringe priority queue, we only need to consider the edges out of a single recent vertex. And we're not having to consider every possible edge that comes out of the white tree so far. Oh, Dijkstra's in this. Sorry, Ben, go ahead. But this is the same thing as running Dijkstra's. It's just with the distance metric as distance from tree rather than distance to source. Exactly. Sorry. Okay. So we can keep running this algorithm if you want. I'm just going to step through. You can do it later if you'd like. And you'll end up with this minimum spanning tree. Okay. But hopefully the idea is clear. Really the important part, you really want to know, did I understand it? It's what happens now? That gets turned into a 4 and so forth. Okay. All right. And of course, I encourage you to step through the rest of the demo later and see if you're happy with it. Let me get this out of the way. All right. Okay. So let me compare Prim's versus Dijkstra's for a moment. So Prim's and Dijkstra's algorithms are exactly the same. It's just that Dijkstra's thinks about the distance from the source vertex, and Prim's considers the distance from the tree that we've built so far. In terms of visitation order, if I ask you what order will the vertices get visited by Dijkstra's, it's going to be in order of distance from the source, and Prim's is going to visit vertices in order of the distance from the MST under construction. When we relax a vertex, when we relax in Dijkstra's, we're considering the total distance from the source versus the total distance from the source that we know so far versus the total distance with the edge we're trying out. So we want to know, does this edge get me a better path from the source to this vertex? And Prim's, it's, does this edge give me a better way to the tree than the old version? Here's a couple little videos of them running side by side. Okay, hold on, let me start them over again. Nope, okay, here we go. So on the right will be Dijkstra's algorithm. On the left will be Prim's algorithm. Okay, so they both start by growing outwards from a central source. But the difference is Dijkstra stays close to home. It's visiting vertices in the order of their distance from the source, whereas Prim's is visiting in order of distance from the tree. So if this algorithm is running and some vertex is really close, it's going to try and visit that vertex soon. Okay. Do they generate the same tree in the end? No, not at all. This right here is the shortest paths tree. It tells you how to drive from this source to any destination vertex with the minimum amount of driving time. If you think of these edges as driving time, Prim's tells you minimum total way to connect all the vertices, which is quite a different object. Okay. Any questions about it? So both of them are a connected tree that slowly grows, and as it grows, it is always connected, just structurally. You never jump around with either of these algorithms. All right. Oops. Nope, stop. Great. In terms of code, what would the code look like to do this? Well, we would create an edge to, distance to, and marked array. We'd have a fringe, which is a priority queue. We would start by setting all the distances to infinity and add all the vertices. Then, as long as the fringe wasn't empty, we would delete the minimum vertex, and then we would scan. What does scan mean? It means relax all the edges coming out of that vertex. Okay, so what does scan look like? First, we mark the edge true to say this is the vertex that's closest, so we're going to add the thing we're scanning from. We're removing it from the fringe, and it's basically committing to say we're done. This vertex is permanently not considered again. Then we'll consider all of our outgoing edges. If we see a vertex that's already marked, we don't need to think about it. If instead the other vertex isn't marked, we'll check, is the path better than what we already know? If so, we update distance to, edge to, and then we move the item up in the priority queue. All right, hard question for you. What's the runtime for this? So assume that all priority queue operations take log v time. I'll let you think about this for a minute, I think. I'll give you 90 seconds to think about it. It's a hard question, but I think a good question. And my hint is just count only the priority queue operations. We use that as my proxy for their overall runtime. Okay, first hint, how many vertices do you need to insert into the priority queue? Here's a hint. How many do you insert? All of them, V of them, okay? How many vertices get deleted from the priority queue? All total. All of them, okay? And how many times, so we have V inserts, we have V deletes, and how many decreased priority operations are there? How many times do you have to, at the worst case, move something around in the priority queue? That's a harder question. What do you think? Let's say I have a graph with 100 vertices and 300 edges in it. How many decreased priority operations could you have roughly? So like 100, 300. What do you feel in your heart? 300. Why? Right. So when you relax an edge, sometimes you're going to be decreasing the priority. So if we want to bound above how many decreased priority operations do we have, it's how many times we consider a purple edge and then cross out that number and write a new number. So in our most vivid imagination, every single edge you look at is going to cross out a number and change it. And that can happen E times. Okay. So what I did here is I just thought about, don't look at the top of the slide. I want to look only at this table. The number of times that I'll add and delete are both exactly V. Every vertex gets added once. Every vertex gets deleted once. And then in the worst case, we'll have E different decreased priority operations. Okay, I said the cost per operation is big O of log V. Why is that? So how many things could the priority queue have in it at most? V. And what's the cost to add an item to a priority queue with V items? Log V. How about deleting? Log V. And change priority? We didn't really talk exactly about how it worked, but log V. So all I need to do is just multiply. If I have E decreased priority operations, and each one's log V, the total amount of time you spend crossing out numbers and writing in new numbers is at worst E log V. Okay, so it's going to be just counting the priority operations. It's V log V plus V log V plus E log V. And if you're lazy and you just say, well, let's assume we have more edges than vertices, which is typical of most interesting problems, then it's going to, well, it has to be actually, because otherwise there's no spanning tree. You need this to be connected. The overall runtime will be E log V, which is the same as Dijkstra's. All right. I said in lab 10. This hasn't been true for like 5 semesters. There you go. Okay. All right. This is a tricky runtime problem, but I think it's a good one to know how to understand. That is, I just count how many times each thing can happen and what the runtime is for each thing, and I get a nice answer, E log V. Any questions about this runtime analysis? Same one we had for Dijkstra's. All right. Don't be too intimidated by this. This, I think, is easier than it might have seemed if your attention drifted. Please ask me later if you want to know more. I got one more spanning tree algorithm I want to teach you called Kruskal's algorithm. So I'm just going to show it to you, and then we'll think about why it's true. In Kruskal's algorithm, it's going to be based on looking out for cycles. We don't want cycles. We're just going to consider the edges in order of increasing weight. So here's all the weight 1 edges. Here's some weight 2 edges, and so forth. And we're going to repeatedly just add each edge to the minimum spanning tree unless there's a cycle. So we'll start by looking at AC just arbitrarily. So is there a cycle in my minimum spanning tree yet? No, there is no spanning tree. So I'm going to add this edge. Okay. What edge should I consider next? Let's say CE. Would this create a cycle if we added it? No, so let's include it. All right. Next, we'll look at DG. Okay. Would this create a cycle if we added it? No. Okay. Next, we look at FG. Would this create a cycle? No. Okay. Now we look at AB. Would this create a cycle? No, no cycles yet. How about this one? Would this create a cycle? Yes. So should we add it? No. All right. How about DE? No. Okay. At this point, we have V minus 1 edges. So we're done. Let's go back real quick. So when we're running this whole algorithm, the cut we're considering is basically all of the, so when I look at this edge, I'm going to treat these two vertices as both white. Why am I treating them as both white? Actually, first thing I should say is, why are C and E different colors when I consider this edge? Well, I mean, I'm not dealing, there is no marking here in this algorithm. I'll give you another one here. Why did I decide to make D white and G green here? So what property are we using to prove that the spanning tree we're building is correct? The cut property. So this is a cut that is consistent with my thinking so far. All right, maybe the most interesting one right here. Like anytime I pick a particular edge, it needs to be that one side is green and one side's white. And if you look at the first so many examples, every time I had one vertex is white, the other one's green. This one, though, I said 2 vertices are white and this one's green. Why would it not really be appropriate to make this vertex green if I'm thinking about this cut? This might be too weird of a thing to be trying to do to you in lecture. Go ahead. I mean, a different way of putting it is like A and C they're part of the minimum spanning tree. So if I color this one white, I should think of this as part of that side of the cut. Right. This is a bit too subtle, I think, for lecture. All right. Okay. So that's Kruskal's algorithm. So why does that work? Like, what's going on? If you followed the coloring, then I think it's trivial. If not, maybe it won't make any sense. But the basic idea is when we pick a new edge and we want to add it, side 1 of the cut will be all vertices connected to V, right? Like whatever vertex, whatever edge we pick, we're going to say, hey, you're V. And then every vertex that's currently connected to V, we're going to all make white. And everything else we're going to leave green. At this point, we know that there's no crossing edges between the whites and the greens. There's no cycles. We don't allow that. And then there's no crossing edge that has lower weight because we're considering the vertices or the edges in increasing order of weight. Now, let's go back to it real quick. I just don't feel like that was clear. Let's try one more time. Okay. So Kruskal's algorithm, I hope mechanically makes sense. We're looking at the edges in increasing order of weight and never adding something if there's a cycle. Let's see, how about this one? So here, I want to prove to you briefly like why I think this 3 is correct. And the way I'm doing it is I'm coloring all of these vertices white. Just not happy with the way I'm talking about this today. But why do you think this is the right coloring to prove that this vertex is, sorry, that this edge is the next edge to include? Someone give me an argument since I'm bombing a little bit on this one. Yeah?
Like you're separating between the white and it's like the crossing edge.
Right. I mean, basically the idea is that I'm going to consider this edge, and the proof I'm going to use that this edge should be included at smallest is going to be to consider these 3 vertices as the green and these 4 as the white. What's special about these 4? Like, how did I know that these should all be colored white? Yeah, they're all connected, right? So they're already connected. So if I think of these as already connected and make those the white vertices, and the ones that are not yet, that are not on this side of the cut, and call these green, then this is the smallest crossing edge. I'm going to hope that explanation was better on the video online. Not happy with it, sorry. Maybe you were happy. Okay. As a last algorithm, I want to show you a slightly optimized version of Kruskal's algorithm. Because one thing I didn't do, earlier we were just eyeballing it to say, is there a cycle? Right? Like I said, I'm going to, why do we not add this edge? There was a cycle, but how do we know if there's a cycle? Well, you have to run like DFS or something. Well, I'm going to show you the version where we use a weighted quick union, which I think is pretty cool. The part I think I poorly explained today is why Kruskal's works. But what I do hope you understand is like what it does. Okay, so here's a slightly different version where again, I'm just going to step through the edges in increasing order of weight. And this time we're going to use a weighted quick union to look out for cycles. Okay, ready? So when we check A and C, are these connected yet? Is there a cycle involving these? No, okay. So we'll add it to the minimum spanning tree and we will also connect them in the weighted quick union object. Next vertex to consider is CE. Okay, are these connected yet? No, so let's add them to the weighted quick union and the minimum spanning tree. Okay. Next, we consider D and G. Are these already connected? No, only AC and E are connected. So then we'll connect D and G, and the minimum spanning tree has D and G in it. Okay. How many different sets are there in my weighted quick union right now? There's ACE, there's DG, and there's actually something else. I'm just not showing them here. What 2 nodes are all by themselves that are not part of any weighted quick union set? B and F, right? Okay. Next, we'll consider FG. Are they already connected? Nope. Okay. A and B, are they already connected? Nope. All right. Now, finally, we get an interesting one. Are E and B already connected? Yeah. And how do you know it? Like based on my data structure. Yeah. Okay. So ACEB, they're all buddies here. Since they're already buddies, E and B, we should not add this to the minimum spanning tree. Which edge do we consider next? What's next in the fringe? DE, okay? Are those already connected? Doesn't look like it. What'll happen to this weighted quick union when we call connected? Or when we connect these 2? There'll be one big set. Okay. And at that point, we're done. So that's Kruskal's algorithm. All right. So let me show you these 2 running side by side real quick so you get an intuition. So Kruskal's and Prim's behave a little different. Prim spiders out over the graph, grabbing the next vertex closest, whereas Kruskal's is doing what? Someone say it in a word. Maybe someone in the back who was a little lost and I was trying to prove that it works. Yeah, what do you think? So in what order are things getting added in crucibles? Shortest. So whatever two things are closest in the graph are getting clustered together. The only time we don't, if we pick an edge and it's really small, when would we not add it? If there's a cycle, right? So notice that crucibles, it's like a distributed algorithm that's building out the whole network bit by bit in a disjointed fashion across the graph. Okay. If all of the edge weights are unique, will we get the same structure in the end? Yes, because there's only one minimum spanning. Okay. All right. Any questions about this? Nope. All right. Okay. Let's talk about the runtime of Kruskal's algorithm. So this is my chance to let you think about this. So even if you're not totally convinced that it worked, here's what the code looks like. Let me walk you through it real quick. The minimum spanning tree is a list of edges. We create a priority queue of edges, and we insert them. In what order will this priority queue be ordered? Smallest edges first. Then we create a weighted quick union object. And then as long as we have more edges to consider, we'll delete the edge. We'll check if these two vertices are connected, like the two ends of the edges. If they are not connected, we'll union them and add the edge to the minimum spanning tree. So think about the priority queue as log v time and weighted quick union operations as big O of log star. I mean, you have a tighter bound than that, but we'll do log star. Good luck. Again, it's how many deletes, how many inserts, how many unions, how many connecteds, how many adds. All right, first question. Is your gut feeling that the priority queue is going to be the bottleneck or the weighted quick union object is going to be the bottleneck? What do you think? Priority queue, why? Yeah, log operations are bigger than this log star business. So you can't totally ignore the weighted quick union object necessarily, but it's probably not where going to be the bottleneck is. This total time, what's the total time to insert all of these edges? What do you think? So you insert E edges into a priority queue, and each one takes big O what time? Log E. So this step right here is E log E, and that turns out it's going to be your bottleneck. Just even inserting the edges at the beginning is going to take a bunch of time. There's the whole table if you want to work through it later, but just inserting and deleting the edges will take you E log E time, and then the union and is connected operations will be relatively quick. So you'll only do V unions because there's only going to be V different edges added to the, or actually just V minus one edges added to the minimum spanning tree. And there are E is connected calls in the worst case, but they're very fast. If these are all the runtimes, different piece of the code, the E log E dominates. It's much faster, or sorry, much slower than these right here. Okay. So I'd say the overall runtime for Kruskal's as we wrote it is E log E. Let's say you already had this data structure built so that the data structure is just in a pre-sorted list and you're not using a priority queue at all. That's just, you have the edges in sorted order. Then it would be the quick union object that dominates. And that, because you wouldn't need to do these top two things at all, if it's already in sorted order, you're not using a priority queue at all, and then it would be E log star. So again, I think this, oh, go ahead. It is the iterated logarithm. This is from the disjoint sets lecture that Justin gave. It's the number of times you have to iteratively take the logarithm before you get to 1. It's a very slow growing function, much slower than log. Yeah, it's effectively constant. Like any number you pick that's normal is gonna, like, it'll basically be 5. Yeah. All right, one last thing I want to mention that's kind of fun is the history of spanning tree algorithms. So there's the algorithm we just came up with was E log V, right? The one that I stepped you through with the demo. You can do better. So there's an algorithm that was discovered in 1975. It's a little more clever. That's E log V. So the log of the log of V. Then there's a exact E log star V algorithm. Now you might say, but wait, didn't we just get an E log star V? Well, that assumed we had a pre-sorted list of edges. This does not assume such a pre-sorted list of edges. Then you could do a little better and say, well, actually, it's the log of the log star of V if you use this 1986 algorithm. And then we start getting to fancier and fancier algorithms, where in 2000, the best algorithm for which we actually know its runtime is E times inverse Ackermann V. And that's an even slower growing function that Justin mentioned. And then in 2002, there's a paper in which they found the optimal minimum spanning tree algorithm, but we actually don't know its runtime. Now, you might wonder how that's possible, that you can have an algorithm that's provably optimal, but we don't know its runtime. It's because they basically pre-cache a bunch of little cases, and they prove that the number of compares is as little as you possibly would ever possibly need, but nobody knows how deep that tree of compares is. We just know that this is exactly as good as it could be. So if you're curious, you can read this paper, which, I mean, it's somewhat, you can read the high-level story, of course, about, they even address this head on, like, how do we know it's optimal if we don't even know its runtime? And they give some thoughts about it. It is unknown whether or not this is linear time, but this is an open question in theory. Can you prove that you have an E time algorithm for a minimum spanning tree? All right, I'm going to close it there. Have a fine spring break, and I will see you next week at office hours. I'm going to hold them, or the week after. See you.